What if I told you that the used oil from an engine is kind of like a blood test for a machine? Seriously, it can tell you everything, its deepest secrets, its hidden problems, and it can even predict when it's about to fail. It's not just some greasy lubricant, it's a liquid story, and we're about to learn how to read it.
It really does sound like something straight out of a detective show, right? How on earth can one tiny drop of oil tell you that a multi-million-dollar engine is about to go down? Well, in this explainer, we're going to go full-on forensic investigator to find out. We're going to follow the clues hidden away in just a single sample of used oil. Okay, first things first. We need to understand how oil basically becomes this secret story buff for a machine. As it's circulating, it's doing way more than just lubricating. It's writing a running diary of everything, and I mean everything, happening on the inside. So here's the key idea you have to grasp. The oil, it's the machine's bloodstream. Think about it. As it flows through every single critical part, it's picking up microscopic clues, tiny fragments of metal, little bits of contaminants, chemical leftovers. It's carrying all this vital evidence, telling us exactly what's going on deep inside. Now, like any good investigation, the absolute first step is to secure clean, uncontaminated evidence. I can't stress this enough. If you get this part wrong, you can just throw the whole analysis out the window. So let's talk about why getting a clean sample is so critical. Look, bad data leads to a bad diagnosis. It is that simple. On one side, you've got false positives. This is when, say, a bit of dust from the air or some gunk from an old sample bottle gets into your new one. All of a sudden, you're on a wild goose chase trying to fix a problem that isn't even there. And on the other side, which might be even worse, you have false negatives. This happens if you take the sample from the wrong spot, like after the filter has already cleaned out all the juicy evidence, or if the machine's off and all the clues have just sunk to the bottom. You end up completely missing a real ticking time bomb. All right, so with a clean sample in hand, our evidence now goes to the lab. This is the fun part, the forensic analysis. This is where we break that oil down and start looking for those elemental clues. And this is where it gets absolutely fascinating. We're not just looking for dirt or something vague like that. Nope, we are hunting for specific chemical elements that act like fingerprints, pointing us directly to the source of a potential problem. So what exactly are these clues we're looking for? Well, analysts basically group all the clues into three main categories. First up, you've got your wear metals. These are the microscopic fingerprints of the machine's parts, literally tiny bits that get shed as components rub together. Second, you have contaminants. You can think of these as the intruders at the crime scene, stuff like dirt, water, or coolant that just shouldn't be in there. And finally, you have additives. These are actually the good guys, chemicals that are put into the oil on purpose to protect the engine. And seeing them disappear can be a huge clue in itself. Okay, let's make this real. Imagine a lab report comes back, and it's flagging high levels of two specific wear metals, iron and chromium. Now, to most of us, that's just a bunch of data. But to an analyst, that's a critical lead. So an analyst pulls up a kind of forensic database, just like this one. They see iron and chromium together. And for a diesel engine, the database points them to one very specific area, the friction between the piston rings and the cylinder liner. And just like that, we've gone from a random clue to a specific crime scene inside the engine. But the best detectives, they don't just look at one clue in isolation. They look for connections. They look for patterns, things that tell a much bigger story. The real breakthroughs happen when all the clues start working together. See, a single data point can be really misleading. Is that little spike in iron a sign of a massive problem, or is it just a one-time thing? A skilled analyst knows you have to look for trends and combinations of data over time to really get to the root cause of what's happening. And this chart illustrates that perfectly. This is what's called a lockstep trend. Here we can see silicone, which is basically just dirt, is rising over time. But look at the aluminum. It's rising at almost the exact same rate. This tells a crystal clear story. Dirt is getting into the engine, and that abrasive dirt is literally grinding away at the aluminum pistons. This isn't a guess, it's a cause and effect relationship written right there in the data. We can even watch a failure happen in slow motion over time. This is a classic example of what's called sequenced wear from a journal bearing. First, we see a big spike in lead. Okay, that's the soft protective overlay of the bearing wearing away. But then, as the damage gets worse, you see the lead signal start to drop off, and a new signal pops up, copper.
That means the wear has chewed right through that first layer and is now eating into the harder bronze structure underneath. We are literally watching the bearing fail, layer by layer, all through the oil.
So, okay, we can find the wear, we can identify the part, we can even figure out the root cause. But let's just step back for a second and look at the big picture. Why is this forensic work so incredibly important? What's the real-world impact of all this? This whole process, it's not just about finding problems that have already happened. It's about predicting the future. The whole point is what's called predictive maintenance, catching these tiny little signs of wear and contamination super early so you can step in before they turn into some catastrophic, super expensive, and maybe even dangerous failure. And the crucial thing to remember is that this isn't guesswork. Labs use these established alarm levels that are based on tons of data. They measure this stuff in parts per million, or ppm. So for iron in a diesel engine, anything below 40 ppm, you're good. That's normal. The machine is happy and healthy. But as that number starts to climb up through the caution zones and it crosses a critical threshold, like 100 parts per million, well, that's when the alarms go off. Big time. This is the moment this whole analysis pays for itself. It is a clear, data-driven, undeniable signal to the maintenance crew to shut things down and take action right now. And that signal, that could be the difference between a simple, cheap repair and having to replace an entire engine. So the next time you see a big truck, a power generator, or some massive piece of industrial equipment, just remember that deep inside, its oil is telling a story of pressure and friction and time. And it kind of makes you wonder, right? What other invisible stories are unfolding all around us, in all the machines that run our world, just waiting for the right detective to come along and read them?